Welcome back. We'll continue the session on how to teach engineering. You saw an example using vibrations with a very simple system, mass spring system. In this session, we'll make it somewhat more complicated and give you some more examples of vibrations. But our primary purpose is to teach you how to teach engineering. What did I miss in the previous lesson? I was talking about amplitude, for example. Amplitude. Some of the technical terms I introduced, I did not explain all of them. I expect you to explain them to the students. Amplitude, usually it's defined from the neutral position to the maximum displacement. For example, in the case of this mass spring system, this is my neutral position. If I've stretched it up to that and let it go, it vibrates. What's the maximum value measured from? Maximum value measured from the neutral position, my reference position. So it will be from 0 to this maximum. On the other side, it's minimum. They are equal. Mathematically, it's going to be this value A. Okay? A, value of A is the maximum amplitude. That's called amplitude. If you mention from this point all the way to this point, which is twice the amplitude, you have to say peak to peak. That's a peak, that's a peak. Unless you mention that, amplitude means 0 all the way to the maximum value. It's only a magnitude. Notice that I'm not saying magnitude or amplitude. That's wrong pronunciation. Amplitude, amplitude, and magnitude. Okay, you've seen this homework also. I hope you assign similar homeworks. Homework should be such that part of it should be directly based on what you have taught. Just to clarify the concept, you have to make them think along the same line using part of the homework. The other thing is to make them think extra, slightly beyond what you have taught, for which they may need to look up the textbook or some other reference and struggle, think. Not everything should be told to them. Spoon feeding is not the right thing to do. Okay, all that you have seen. Now let's continue. What other kinds of vibration? We have seen only a spring and a mass going up and down. Rarely ever you encounter such simple problems. Usually a whole structure vibrates, but using that simple mass spring, one can model a lot of complicated structures. You may have to use many masses and many springs. Okay, so if you study mass spring very well, understand that fully, you should be able to extend that to model any complicated system. All right, there are other kinds of vibration. For example, what is this doing? This is an animation of a cantilever beam. Cantilever means one side of the beam is fixed, that's hanging. Now this one can vibrate like that. That's going to be bending vibration. It bends. But what you are seeing here is torsional. Look, it's twisting. Beam is twisting like that. Okay, long beams can vibrate like this, can vibrate in various shapes. Those are called mode shapes. It can twist, that's torsional. Also, it can vibrate back and forth. Okay, if I hit it with a hammer like this, there will be vibration that's compressing the and extending the beam. That's longitudinal. Along the axis, if vibration, the displacement is perpendicular to that axis, it's going to be transverse vibration. For example, let's say sound wave. Okay, sound waves. Waves Sound, electric circuit, earthquake, all these things are very similar to vibration. Okay. Waves, let's say sound. Okay, that's some kind of wave. What is happening there is air is being compressed and decompressed. Compression and expansion, compression, expansion. A wave propagates in that direction. Whereas in electromagnetic waves, it's not the same. Electromagnetic wave, you can say the field, electric field is vibrating that way, magnetic field that way, and perpendicular to both of them, the electromagnetic wave propagates. All right. Earthquake, that's also vibration. Because of some reasons, let's say the plates shifting or volcano erupting, there's vibration caused. And that vibration travels as waves through the surface, also under the ground. Different kinds of waves, okay, Rayleigh waves, shear waves, etc. But all these things are related, okay. All right. Building, vibration. Tall buildings do vibrate. Okay. Even simple things like atoms. In my earlier videos, I showed large structures like bridges, airplanes vibrating. But even atoms vibrate, okay? Equations are similar. String theory, what does that mean, string theory? This is one of the modern theories in physics that tries to explain everything. Theory of everything. This is one of the candidates. Not been proven because no experiments can be done till now to prove that. But that says everything is made of vibrating strings of energy. Okay? Different modes manifest as different particles. Okay, so vibration is very important. It's not only large structures, even smallest things. Every particle can have vibration. Crystals, for example, it vibrates. You know, the quartz crystal that's used for timer vibrates. Okay, beam bending vibration homework. We'll have to assign some homework, which is more complicated than just that mass spring. So let's take one. You cannot derive the formulas for vibrations of everything. You derive one or two. Rest of them, they should be able to, using similar concepts, should be able to look up a handbook on vibration or their textbook, get the formulas and apply it correctly to solve the problem. For example, here I have given a beam vibration problem. Okay, here's a beam that can vibrate like this, bends like this, let's say the red line, and then it flips to the other side and goes like that. Okay, now the same beam at a higher frequency can vibrate in another mode, which is represented by this green line. What that means is instead of just going up and down like this, one part goes down, another part comes up, and then it flips to the other side. One part, this part which is down, goes up, and this tip comes down and vibrates. That's a different mode, and that's called mode shape. Okay. Third mode, which is even higher mode with higher frequency, would have this kind of shape. A part goes up, then it goes, another part goes down, then the tip comes up, then it flips. Okay, this part comes down, that part goes up, and the tip comes down. So higher mode and higher frequency. So different shapes in continuous, this kind of continuous structure that can happen. Okay, so cantilever beam. First, the first three natural frequencies. You can explain what natural frequencies is. You know, that omega n, omega we are talking about, that's natural frequency. Why is it called natural? Explain. You find out and explain. Okay. Remove the damping and the force vibration. Stay with the natural frequency first. Given 1 meter solid steel beam, cross 1 meter long, okay, quite long, but the cross section is very small, 1 centimeter by 1 centimeter rectangle. Okay, this is how it's written: 1 centimeter by 1 centimeter cross section. Okay, density of steel is given because we know it's related to mass and stiffness. All the vibrations are related to that, so we give rho, which is density of steel, okay, 7,800 kilograms per cubic meter. Elastic constant or Young's modulus, I did not supply that. Let them look it up. Let them find it from some standard books or handbook. Okay. Now, formula, I have taken it from some standard book. This is the frequency, which is, the angular frequency divided by 2 pi. N represents the mode, first mode, second mode, third mode, etc. Frequencies are going to be different. Higher the mode, higher the frequency, equals some parameter, beta n squared divided by 2 pi, and then L squared, length of the beam, squared, square root of EI by rho A. EI represents some kind of stiffness, bending stiffness, okay? E is this E, I is moment of inertia, this 1 centimeter by 1 centimeter. Ask them to find out how much it's going to be. Moment of inertia about the central axis, because that's about that axis it bends, okay? And then EI will give stiffness, then rho is the density given, A is the area, cross-sectional area. Now notice that this part is similar to K, elastic constant, and this part is similar to mass. Okay, here it's mass per unit length. Okay, there is also an extra parameter, L squared, that comes outside. Even if I put an L over there, this goes over there, still there will be some L raised to the power something left there. That's because it's actually a long beam, the bending and the stiffness depends quite a bit on the length, and notice that L is the denominator. That means higher, longer the beam, smaller the frequency. Okay, short beam, high frequency. These things from the formula one should have in their mind. They should interpret it correctly. Okay, beta 1, these values are given. Beta 1, these are theoretically derived. Beta 2 is that. Beta 3 is that. 3 frequencies they have to calculate. Okay, do you notice that EI is the stiffness and rho AL, if I put that, that will be the mass of the beam. But still there's going to be extra L left here. Similar to, but this part is similar to square root of K over M. Stiffness divided by mass. All right, so you'll encounter this or similar terms in finding the frequency in almost all vibration problems, mechanical vibration problems. Okay, now E, where would they get E from? From a book. Some of the students will ask, which steel, sir? You didn't tell which steel to take. There are hundreds of different types of steel. Why didn't I mention what kind of steel? Can anyone answer? All of you are physics and engineering professors. The elastic constant of steel is almost the same for all kinds of steel. Almost the same. Okay? Did you know that? You should know that. Okay? The strength may vary a lot by a factor of maybe 5. If you take mild steel to high strength steel, it may vary quite a bit. But elastic constant remains almost the same for all steel. So you should know these things. These things are very practical. Usually in industries you learn that. Okay, so let them calculate that. Now what is the relation between circular frequency, and time period? You should ask these questions too, probably as homework. Let them find out. Cycles per second is the F, these frequencies. Okay, these things is radian per second. Okay. Now, cycles per second is also called Hertz. Hertz is another name. Hertz was the name of a scientist. They should look up who was that scientist. A physicist, very famous physicist from Germany, Heinrich Hertz. Let them read about that. A little bit of extra knowledge. Maybe they'll get something motivational from his life. What is mode? You have to explain what are these modes. I casually explained it to you, but you should probably try to make it a little bit more specific. Let them write 2 lines about it by doing some research. Plot the mode shapes. I have already plotted by hand here. Okay, for example, for the example beam. All right, good. Let them do these things as homework. Okay, do not do everything for them. Plot how frequency changes with length. So if the length changes, let's say from 0.25, short beam, and then 0.35, 0.45, etc., you can ask them to calculate all the way to 2 meters and plot it. Because L is in the denominator, L squared here, you'll see the variation. If you make the beam longer, the frequency will drop. The natural frequency will drop. Okay? This is all natural frequency, its own frequency of vibration. Read about damping, forced vibration. Assign these things ahead of time. Before the next class, they should come a little bit prepared with these things. They may not understand everything. They may have questions for that. About that, some of the things they may not understand, but let them read and come to the class somewhat prepared. Then it will be easy to explain to them. Is spinning of a wheel vibration? All these things you can assign as homework. Explain in simple words. Spinning. A wheel is spinning. If you put a dot on the wheel, it's repeating the motion, right? After every cycle, it's repeating the motion. Is that vibration? Why not? Why not? Think about it. Think about it. Make the students think about it. All right. That's it. There could be vibration like this, torsional we have seen, but if it's just going in circular motion, it's also repeating the motion. But that's not vibration. Why not? One has to think a lot and find out, what is this vibration? Is it variation of change, variation in acceleration? What is vibration? How do you precisely define? All right. Vibration occurs. These are basic things one should know. So summarize this towards the end. Vibration occurs because of an applied force or displacement, and an elastic force that tries to restore the body to equilibrium position. There's some displacement, some force has been applied, displaces from the neutral position, and there's an elastic force that tries to bring it back. So it's different from frictional force. That doesn't try to restore it. It opposes the motion, but doesn't try to restore it back to the original position. So friction does not cause vibration. In fact, it reduces it. Okay, they should think about these things. The restoring force is proportional to the displacement. So it's different from friction. They should know that. Okay? It doesn't have to be exactly linearly proportional. That somehow proportional. That will also cause vibration. But generally, it's linearly elastic. So proportional to the displacement. The applied force or displacement, mass and stiffness play the most important roles. Of course, the structure, the type of structure, then the applied force or displacement, mass and stiffness. These are the most important parameters in vibration. Energy is repeatedly converted between potential and kinetic forms. Do you understand that? Something is vibrating. At this point, it stopped. What happened to the energy? All got stored in the spring as spring's potential energy, which is half k x squared. Okay, why? Because it starts, force is proportional to the displacement, so it's a triangular shape, kx. If you integrate that, you get triangle. So that's why half comes. Okay, all right. Area under the triangle. Now, that energy, as soon as it starts pulling, the speed, the mass increases from 0 to a maximum value. At that point, at the center point, the spring has no more energy because it's not stretched anymore. Okay, so all that potential energy got converted back into the kinetic energy of the mass. So constantly, kinetic and potential energy are being exchanged. All right. Vibration analysis is important in designing cars, planes, trains, machines, buildings, bridges. These are the general concepts they should remember. They should have there in their mind where to apply a vibration problem. Just because something's moving doesn't mean it's a vibration problem. It may be something else. Okay? But they should know that these are very important. Vibration analysis is important in designing all these things. In nature, simple harmonic motion is rare. Rarely you'll find something just nicely vibrating like this or vibrating just like this. Usually it's the combination of several modes and also some noise. Okay? So very rarely something would in the nature would vibrate just in one mode like this. It's going to vibrate in a way which is combination of all three modes. 3, 4, 5, 6, 7 modes. Okay? Combination of many modes with different amplitudes. Also, there's going to be noise. There could be random vibration. All that. They should know that. Okay? We are simplifying it using one mode because it's easy to analyze. Finally, it's going to be a combination of many modes. Homework. Come up with a homework that's very realistic, something they can experiment with, feel, measure, calculate. Okay, something. It could be a tall building. It could be something simple like take a harmonica and look at the reeds over there and say they are different length, and let them vibrate one of them either by blowing on it or just by plucking on it, and you would see that this one produces probably low frequency, slightly more like bass, and there's higher frequency. Because of that cantilever, the length is the denominator. Shorter the length, higher is the frequency. These all correspond to different nodes, right? Different note, musical notes. So higher frequency, higher note. Shorter the length. They would be amazed that whatever they learned just in that homework is being actually applied for hundreds of years in creating musical instruments. Let them measure the length and try to calculate the frequency. Let them be creative. There may be some app that can measure the frequency. Okay, give it the sound, it can tell you roughly what frequency it is. Okay. All right. Length and frequency of the reeds. Study that. Let them do whatever they can. Not everybody will do exactly what you want, but that's okay. Let them explore. Now, how to control vibration? Vibration can be useful, like musical instruments. We have seen vibration can be catastrophic, or at least annoying noise, etc. How do you control that? From the design, you play with the structure's design. You play with its stiffness, mass distribution. You can control vibration to an extent. Damping, you can introduce something called damping. Okay, some of the cylinders, liquid, they are dampers. For example, car suspension. It's got spring, either coil spring or leaf spring, and dampers. Sometimes dampers and springs are built into one system. Okay, dampers, viscous damping they use. One could use probably frictional damping too. Okay, damper, that reduces the vibration. Active control, suppose a building is moving, swaying this way or that way, you could use something at the bottom to reduce that. Okay, some kind of active mechanism to reduce that vibration, or something on top, a moving mass. You could use a motor and a control system and actively control vibration. Okay, so there are different methods of doing it. Just studying that there is a problem, this can cause problems, is not enough. How can we overcome that? Because now we understand it's easier for us to design something to overcome that problem. Okay, project, solve the bus jerk problem. This problem has been in my mind for a long time. For some countries, for example, in India, on the roads, sometimes you have something called speed breakers. In the US, it's called hump. Or there could be ditch, hole. Okay, suppose a bus drives over it, but the driver slows down, and the front wheels go over this bump very nicely and slowly. Then the driver just accelerates. So by the time the rear wheel comes to this speed breaker or hump, the bus has quite a bit of speed and it goes over it. At a higher speed, it gives a huge jerk. A lot of Passengers sitting in the back feel very uncomfortable. The bus driver doesn't know that and doesn't even care, I suppose. Many of them don't. How do you solve that problem? The suffering of all these passengers. Or suppose you're transporting something with truck. It may get damaged because of that. The driver probably doesn't know or doesn't care. How do you solve that? So, assign some project based on whatever they are learning. Let them think about it. By the time you're finished with the course, they'll have a design ready. They can test it, create something, test it, and if it's possible, patent that design. Can manufacture it or sell it to some company, truck or bus manufacturer company. It can happen in cars too, but maybe trucks or buses are more important because it's quite far away, the distance between the wheels. So how do you solve that? One of the simplest ways to do it, you can assign it to your students and see if somebody can come up with this design. The bus should detect, there should be sensors that detects that, okay, the front wheel went over a bump or a ditch. You know how many rotations the rear wheels will take to reach that point. Till that time, do not let the bus accelerate using some electronic controls. Even if the driver presses the accelerator, it will not accelerate much. It will not pick up high speed. After the rear wheels have crossed the same position, then it's allowed to accelerate at a higher speed, to a higher speed. Okay? It's possible. I'm just giving you an idea. One can refine this idea and come up with something even better. More sensors. Okay? But that's the thing. This is going to be some sort of, in a way, indirect active control. Instead of training thousands of bus drivers how to drive carefully and care about the comfort of the passengers, it's a simple device one can create. All right. Show a video of Tacoma Bridge, which I have done. Tall building, swinging, I have not shown yet, but you can find one. Earthquake, building swaying after the earthquake or during the earthquake. Search for such videos and show it to them. Tacoma Bridge I have shown, airplane I have shown. Okay, now, in many real-life mechanical designs, one must consider static loads and dynamic loads. Just making something statically strong enough is not good enough. Firstly, the cost would go up. Also, dynamic loads, if you don't consider that, because remember, even if you make it strong, mass is an important parameter. Mass and stiffness, both. Okay, so optimum design one has to seek. Dynamic loads one has to consider. If there is a possibility of some kind of vibration, one has to study that. Later show that it's not going to be damaging. It's safe against the vibration, dynamic loads, dynamic behavior, okay? Many people design something and they forget to take care of this, and suddenly it vibrates and breaks. Then they wonder, why did that happen? Well, you forgot to take care of the vibration. Vibration is very important, all right? Question and answer. If you have any questions, please submit to me in the comment section. I'll try to answer, or you find the answer, your professors. Do the same to the students. Ask them to come up with some questions. Try to find the answer. Ask them to find the answer. If they cannot, they can have a group discussion. Somebody can come up with an answer. If not, then you, as the teacher and professor, look into it and see what can be done. Please do not discourage the students. Let them explore, think, and create. ETC, that's one of the best things to do to the students. Let them explore, think, and create. They can create thousands and thousands of solutions, wonderful products, and solve problems. Okay? Thank you very much.